a few additional things from where we have left. Okay. And all right. So we have covered a lot of ground with respect to deep learning. We try to understand what is a neural network, what do you mean by input layer, hidden layers, and output layer. We also try to understand on how many neurons you would have in the input layer. How do we decide on how many neurons we are going to have on the output layer, and how many hidden layers we need to have. We have kind of understood those aspects. And within each neuron, we have integration component and activation component. This is also something that we have discussed. And also, we have understood backpropagation algorithm, which is used to update the weights. And we have also tried to understand optimization techniques, gradient descent algorithms, batch gradient descent, stochastic gradient descent, mini batch stochastic gradient descent. And then we will now understand about different activation functions which exist. And why do we actually have those activation functions? And what activation functions are preferred depending on whether your output variable is continuous or depending on whether your output variable is categorical, two categories or not. So this is what we would do today. And we will get into some amount of deep learning regularization techniques. We'll understand how multi-layered perceptron works and the math behind the scenes. When we get to the practical aspects, trust me, it'll be walk in the park. Okay, because all these things you would have known by then, just by putting those options in the algorithm, your job would be done. Okay. So what are we waiting for? Let's get started. Good afternoon, everyone, and welcome back to the session. So a quick recap. We have understood CRISP-MLQ framework. We understood that this framework has 6 phases, phase 1, 2, 3, 4, 5, and 6. And we also understood that we would talk predominantly about model building. And within this, we would be predominantly, once again, be talking about deep learning. Within deep learning, we'd be talking about neural network algorithms. This is what our focus would be. Okay. However, I wish to do some recap of the concepts that we have discussed using Q&A. Okay, there'll be some quick Q&A, which will serve 2 purposes. One, I will understand whether you're understanding or not. Second thing is it will also trigger the internalization process and also help us remember a few things. So let me go here and let me put up a poll question. And go here and put a poll question here. My question is, if you all are able to see the screen, either I'll share with you the link, answer there, or you might want to resort to the chat window here itself and answer. Either way works. But if you answer here the poll question, it will also be recorded, right, for your future purpose. Okay, the question here is, how many neurons should we have in input layer? Okay, we're now trying to understand entire, the neuron stuff that we have spoken about. Option 1 is as many features or, sorry, something really went wrong. My bad. Okay. How many neurons will we have in input layer equal to number of features, or is it going to be equal to number of observations? Okay, and I think this should do. The number of observations, but it's not taking more than that. Let me put it this way. Okay, here we go. I'm posting this for deep learning and AI. Okay, so there we go, so that it reaches you. And I'll also copy this link and post it here. I request everyone to please respond, and then I'll give you my answer. I'll certainly give you my answer. This is one thing. Second poll question would be, how many hidden layers should we have in MLP, multi-layered perceptron? 3, 1, as many as you wish to. Okay, so I'll enable it for a week. Okay, that's fine. How many hidden layers should we have in MLP? This is the next question. Once again, this is for deep learning and AI. Okay, let me copy this and keep it handy. Okay, so let me just present. All right. This is a second poll that we have. And the third poll would be, how many neurons should we have in each of the hidden layers? 4, should it be 3, or should it be as many as we wish to? Okay. Next question is, will we have activation functions in the input layer neurons? Yes or a no? Yep. So these are a few questions, friends. Please respond. I have already given you the poll question option to take these questions, right? All right. Now we will look at the first question, and please respond. I mean, that's a link. I mean, that's okay. You can be active on social media. Okay. The first question is, how many neurons will we have in input layer? Yes, friends, doctors, professors, students, whoever are attending. What do you think? How many neurons will we have in the input layer? Yep. Go for it. Is it A or is it B? I'm making it even more easy for you. Should it be A or should it be B? Yeah, please answer, everyone, please. Resort to the chat window and respond. Seems like there is a lag also, but yep, absolutely. So the number of neurons in the input layer will be equivalent to number of features, my dear friends. So if you look at the number of neurons, yesterday we have already discussed that if you have an output variable and input variables, okay, x1, x2, x3, x4. If you have 4 inputs, you'll have 4 neurons. So the number of neurons is equal to the number of features. Okay, please remember this, that the answer is equal to number of features. Next question. How many hidden layers should we have in MLP? Yep. What is your answer if I were to say that this is A, this is B, and this is C? Let me also zoom in. Maybe people are connecting on mobile. Maybe you're not able to see. So this is the question. How many hidden layers should we have in MLP? A, B, and C. Yep. Okay. Let me wait and see if I get the required responses. Yes, absolutely. Majority wins. As many as you wish. Hence, the number of hidden layers within MLP is called as a hyperparameter. Okay, it's a hyperparameter. Hyperparameters are those options which can be tweaked and experimented. Okay. So there is another question, which is this. How many neurons should we have in each of the hidden layers? And once again, I'll give you the options A, B, and C. Yep. I expect a sizable number of people to at least respond, please. Yes, wonderful. A few of y'all are getting it right, and the right answer happens to be C. Number of hidden layers and the number of neurons within the hidden layers can be as many as possible. So once again, it is not just the number of hidden layers, but the number of neurons within the hidden layers are also the hyperparameters. Okay. The next question seems to be fairly straightforward. Yep. Will we have activation functions in the input layer neurons? What do you think? Okay. So majority of you are saying no, and that's the right answer. Okay, that happens to be the right answer. So you cannot have, simple. You would not have, rather, if I were to put it that way. Okay, so back to our discussion here. So when you have your neural network, you will have your input layer. And how many neurons will you have in your input layer? Input layer contains number of neurons which are equivalent to the number of inputs, or the number of features that we have. And then we have hidden layers. You can have as many hidden layers as possible and as many neurons in the hidden layers as possible. There's no limit as such. So the number of hidden layers and the number of neurons in each of the hidden layers can be as many as possible. Then each hidden layer will have an integration component and an activation component. Each of those will have integration component and activation component. Then you have an output layer. Output layer would contain two components. Once again, the integration component and activation component. Okay, so that's how it works. All right. This is your output layer. So we have input layer, hidden layer, and output layer. Except for your input layer, all the other layer, neurons, will have both the integration and activation component. And we also understood that initial set of hidden layers will capture low-level details. Next set of hidden layers will capture mid-level features. Next set of hidden layers will capture high-level details. And then you have your output layer, post which you will have your output. And say you have your output layer and hidden layer and output layer. The usage of activation functions within the neuron is to ensure that the nonlinear patterns are captured. So obviously, we need to use activation functions which bring in the nonlinear aspects into picture. That nonlinearity should be captured. Okay, and that's the reason why, that's the reason why we capture nonlinear patterns, or the model captures nonlinear patterns. The activation function in the output neuron, output layer neuron, really depends. Okay, it can be any of the neurons depending on what your output variable is. We'll get there. We'll also talk about that. So now first, let's try to understand a few of the activation functions. You have identity function, which is also called as a linear function. Linear function doesn't do anything, friends. It will just take the, suppose in your output layer, you have used the activation function, which is linear, or identity function. Say you have used linear or identity function. This linear or identity function ensures that it takes your integration component and passes the integration component as is to the function. And this activation function linear identity also will ensure that it gives you the same output. If the integration is 0.8, output would be 0.8. So linear function doesn't do anything. Linear or identity function doesn't do anything. It will just take the input and say that this is only going to be the output as well. Okay, so that's how it works. All right. And remember one more thing, that when your output variable is continuous, then the output layer activation function would be linear or identity. Okay, so let me erase this and let's move on to the other functions. And there are a lot of other functions which exist, such as you have step function. If the neuron, if the integration value for that case, okay, is less than 0, then the output will be 0. This is 0. This is 1. If the integration value is going to be less than 0, then the output would be 0. If the integration value is going to be greater than 0, equal to or greater than 0, then the output would be equivalent to 1. That's step function. Then you have ramp function. In ramp function also you have 0, 1, etc. And if the integration value is going to be less than 1, then the output which your ramp function would give would be 0. If the integration value is going to be greater than 1, then the output would be equivalent to 1. If the integration value is going to be anywhere between 0 to 1, then the exact value will come out as an output. For example, if the integration value happens to be 0.7, if this integration value happens to be 0.7, then the output also would be 0.7. If the integration value is going to be 0.9, then the output also would be 0.9 within this range. If the integration values are in between 0 to 1, that's how it behaves. Okay, next. The challenge with respect to both of these step functions as well as ramp functions is that you have a steep bend. That steep bend is also called as a cusp. Whenever you have that steep bend, you'll have a single value over there. And whenever you have a single value, the integration pertaining to that single value is always going to be 0. Whenever you have sharp cusps, sharp kink, there are multiple names to that, then integration at those points would be equivalent to 0. Hence, people prefer a smooth curve like that. Yeah, it's like a ramp function only. The only difference is that you have that smooth finish. Okay. And no matter what your integration values are, it can be integration values can be anywhere between minus infinity to plus infinity. It doesn't really matter. Okay. But your output values of sigmoid activation function would always be in the range of 0 to 1. So sigmoid function is going to clamp. It's going to clamp the values to the range of 0 to 1. Next. So we have sigmoid and we also have tanh. Tanh stands for hyperbolic tangent. Okay. So when it comes to hyperbolic tangent, this also belongs to the smooth family. These are all part of smooth family, sigmoid, tanh, etc. And here, the values will lie in the range of -1 to +1. Okay, tanh values will lie in the range of -1 to +1. So for a neuron, you'll have integration and activation, except for input layer neurons. All the other layer neurons will have both integration and activation components. Okay, and here, when it comes to the activation, if you use tanh, hyperbolic tangent, then no matter what your integration values are, outputs will be in the range of -1 to +1. So what tanh does is it will take your inputs, which are the integration values, whatever those values are in the range of, doesn't matter. They're going to be squashed into the range of -1 to +1. Then you have ReLU, which is rectified linear unit. Okay, you have ReLU, which is rectified linear unit. ReLU, for some reason, has been working exceptionally well. And ReLU activation functions have been giving very good results. And ReLU activation functions are extremely widely used in the hidden layers. So you have your input layer, you'll have your hidden layer and your output layer. Input layer would not have any integration and activation components. Hidden layers would have. Hidden layers will have integration and activation components. And also your output layer. I'm saying that ReLU activation functions are more preferred in your hidden layers. And whenever you have images to deal with, ReLU activation functions are very widely used. Okay. How does ReLU activation function work? It takes maximum of 0 and x. So that means no matter what your integration values are, output when you use ReLU would give you either 0 or your x value. So for example, your integration value, for example, happens to be say 10.1. So you need to figure out what is the maximum value, 0 or this x, 10.1. If 10 point, obviously 10.1 is the maximum, so that would be your output. Okay. So sorry, just a quick moment. Okay. So if you get, sorry, some disturbance. Okay. If you get, for example, 6.2, what is the maximum of 0 and 6.2? Obviously, it is 6.2. So you put 6.2 as output. If the integration value is minus 1.3, what is the maximum value between 0 and minus 1.3? 0. So the output would be 0. Okay, so always the minimum value that you're going to have in ReLU is 0. But a few people thought negative values also make sense. If negative values also make sense, then why can't we give some weightage to the negative values? For example, here we are giving 10% weightage or 1% weightage to the negative values. So you're not completely saying that if you get a negative value, let me make it 0. You're not doing that. If you have a negative value, multiply it with a small factor so that the negative values are also included in your output. And this variant of ReLU is called as leaky ReLU. Okay, so a small variant of ReLU is leaky ReLU. And here also you have a sharp cusp, right? If you're going to have a smooth curve over there, that would be called as ELU, exponential linear unit. Okay, exponential linear unit. There's that curve over there, small curve. That's called as ELU. Okay, this is also called as slightly shifted ReLU, right? You're shifting it down and you're taking it towards the left, slightly. Next. If you just have additions and multiplications in your neural network, ultimately what will happen is the network will collapse to a single number. That's called as network collapse. To prevent this kind of a network collapse, people try to use activation functions which are non-linear in format. Okay, that's going to prevent the collapse of the network. There are a few more activation functions, such as you have state step function used in perceptron. You have unit step function, Heaviside step, sine type 1, sine type 2. ReLU, we already discussed, leaky ReLU. We have parameterized ReLU. You have shifted ReLU. You have max out. Max out would help you figure out the maximum value. For example, in your neuron, you'll have integration component and activation component. What do you mean by integration component? If you have your inputs, then if you have weights, W1, W2, W3, X1 into W1, X2 into W2, X3 into W3, in that way, when you multiply, of course, you'll also have a bias called B. Then you integrate, right? You get some number. Say for that a specific number, which one do I need to fix to explain you? Okay, let me pick a number here. Okay, you got a number here. For that number, You can have a value, this value, or you can have this value, or you can have this value. Okay. For this, you can have any of these values as your output. Max out function always picks the maximum value. This is the maximum value. Between this, this, and this is the maximum value. So that would be spilled out as an output. That is about your max out. Okay. And one more time, if I were to explain, if you have, or if you're going to use only linear activation functions throughout, integration, activation, integration, activation, integration, and activation. If the activation functions are going to be linear functions, then what would you have? Only multiplication and addition, x3, w1, w2, w3. To get this integration function, what do you do? It's going to be b plus w1 x1 plus w2 x2 plus w3 x3, so on and so forth, right? And then you get this. Then if it's linear function, the same value will go out. And here also same would happen. If you use a linear function, whatever is the integration, the same thing will go out. When this happens, people say that your network is going to collapse. When your network collapses, what happens is your learning stops. So that means if you have a larger network, your network might somewhere in between itself collapse. That means your training will stop. If you look at your loss function or cost function, this is how it appears, right? If your weights are randomly chosen, and if you have your loss function or cost function, which is here, then through back propagation, your weights are updated to minimize your loss. Again, your weights are updated to do what? To minimize your loss. Again, your weights are updated to minimize your loss. And then you get to the minima. But if your network collapses, if you use linear activation functions in your hidden layer, your network collapses and probably your training will stop here. Your training will not proceed further. That's the problem with respect to linear functions. Hence, people use nonlinear functions, and all these are examples of nonlinear functions. I mean, linear means straight line, but this is piecewise linear. This is linear, but together it's not linear. So together we have to see, not piecewise linear. Okay. Then we have a few other functions called as soft plus, which is a smoothened version of ReLU. ReLU would be like this. If you just smoothen it, it becomes soft plus. ELU we have already discussed, sigmoid we discussed, tanh we discussed, right? And then we have something called as swish, which is combination of ReLU and ELU, wherein you have a small bump like that. And we also have soft max function. So when you are output variable is continuous, we use in the output layer neuron, we use linear function or identity function. If your output variable is discrete, and if you have two categories, then in the output layer neuron, you're going to have sigmoid or tanh. If your output variable is discrete, and if you're going to have more than two categories, then you're going to use softmax activation function. If output is continuous, linear identity function in your output layer neuron. If output variable is discrete in two categories, you either use sigmoid or tanh. If the output variable is discrete in more than two categories, we use softmax. Okay. So these are the bunch of activation functions that we have. And here you have the difference between sigmoid and tanh. Sigmoid would give you the values in the range of 0 to 1. Tanh will give you the values in the range of -1 to +1. Okay. So that's about the activation functions. Now let me show you a specific nice image. Okay, there pause here. I pause it now. Let me show you. So, okay, I'm just, yeah, I found it. So let me play this for y'all. I'll put it onto the LinkedIn and also on our website. So have a look at this, please. These are all the various activation functions that we have discussed about. Then we have piecewise linear functions, leaky ReLU, parameterized ReLU, shifted ReLU, then max out, right? Then we also have smooth functions such as soft plus, like ELU, sigmoid, hyperbolic tangent, swish. And then finally, we also have softmax function. Okay. So when it comes to softmax, I wish to talk more. Okay. And I would probably take another 5 minutes to quickly, explain about this. Okay. If your output variable is categorical, and if you have two categories, two classes, such as, will a person who has applied for the loan default or not default? Okay, will a person default or not default? Say that's what you are interested in. In this kind of a scenario, say you have your input layer, output layer, hidden layer and output layer. And you have all those connections. Okay, so now here, output would be a number. Okay, and usually when it comes to output variable, which is categorical in two categories, we use sigmoid. And what does sigmoid do? Whatever be the integration value, when you give it to your activation function, sigmoid will squash the values into the range of 0 to 1. Okay, sigmoid is going to squash the values into the range of 0 to 1. Now, we also know for a fact that probabilities are going to be in the range of 0 to 1. So probabilities are going to be in the range of 0 to 1. And sigmoid also would give you values in the range of 0 to 1. So if the sigmoid is going to spill out the result and say that output is going to be 0.9, you can say that there's 90% probability that a person will default. Default means 1, not default means 0. The closer the value is to 1, the higher is the probability that a person will default. Then we have not default also, right? And here, usually people take a cutoff as 50%, 0.5. If the final output is greater than 0.5, then you say that person will default. And if the value is going to be less than or equal to 0.5, you say that person will not default. Okay, so default or not default. Then, this is with respect to output variable categorical in two classes. Let me erase this and let's take an example of 3 classes. Would a person repay the loan on time, or will a person repay the loan with a delay, or will the person default completely, right? Say there are 3 classes. So if you have your output variable, which is going to be more than 2 classes, say 3 classes, is a person going to repay the loan with a delay, or will a person pay ahead of time, or will a person be a willful defaulter? In this case, sigmoid doesn't make sense because sigmoid will give you the values in the range of 0 to 1. Okay, and sigmoid is used when you have 2 classes. Because when you get values in the range of 0 to 1, they are like probabilities, hence. Okay, so here, each of these values that you get after the integration and whatever be the activation function that you use, ultimately the values that you get right would not equal to 1. those values will not be equivalent to 1 when you add them. But why should they add up to 1? Might be a question. Say, for example, you got a value 0.8 here, you got a value 0.4, you got a value 0.3. When you add these three numbers, how much do you get? 1.5. This is what you get. And if you look at probabilities, if you have head and a tail, probability of getting a head when you toss a coin is 0.5, probability of getting a tail is 0.5. When you add these, you get 1. So the summation of probabilities of all the events will always be equivalent to 1. Okay, it will always be equivalent to 1. But in this scenario, it is not going to be 1 if you have more than 2 classes and if you use some other activation function. To ensure that you convert all of these numbers into probabilities, we use an activation function here. And this activation function is called as softmax. What is the role of the softmax? The role of softmax is to normalize these values and ensure that the outputs that you get for these three are going to be some numbers. But when you add up those numbers, the summation will be equivalent to 1. The moment the summation of all the values are going to be equivalent to 1, you know that they are probability values. Okay, so that is why when you have more than 2 categories, we use softmax, and that is the purpose of softmax. So quick question for you all. What activation function is used in output layer when output variable is continuous? Yep. What do you think is the answer, friends? Please use the chat window and answer. And okay, absolutely. Right? It is linear function or identity function. Wonderful. So we use linear function or identity function. Okay. Next. What activation function do we use when your output variable is discrete or categorical in 2 classes? Is it only sigmoid? Or can I use something else? Or tangent, hyperbolic tangent. Absolutely, bang on. What if your output variable is discrete in more than 2 categories or more than 2 classes? We use softmax. So now you understand the entire deep learning neural network, right? How many neurons you should have in the input layer? How many hidden layers you can have? How many neurons in hidden layers can you have? How many neurons should we have in the output layer? What should be the activation functions of the output neuron, output layer neurons? For the hidden layers, usually people use ReLU or the family pertaining to ReLU that actually is giving amazing results. So you all also can simply start using ReLU activation functions. For the neurons within the hidden layer, obviously you won't use softmax, right? But you can also use sigmoid, tanh, etc. But ReLU works very well. In almost 90% of experiments, one of the research articles says that ReLU activation functions, when you use those in the hidden layer neurons, then it gives you amazing results. Okay. Now, suppose you have X and Y, 2 neurons, and suppose you have a hidden layer which has 3 neurons. So each hidden layer is like a perceptron. Each hidden layer neuron is actually giving you one line, linear line like that. Okay, and then ultimately you combine all of those. If you have one layer here, L1, another L2, another L3, then when all of those overlap, you get one final output. Okay, all right. Now let's look at the cost function or the loss function. Sometimes you call it as error also, but then there is a thin line of difference between error function and cost and loss function. All right. Anyways, we are aware of the difference between loss function and cost function. Now, again, I have some questions for you. Because we are now talking about error function, loss function or cost function. Loss function is for every observation that you send to your network. When you aggregate that, you get the cost function. But which one should I use? How do I evaluate? Here, if your output variable is continuous, we use a measure called as mean absolute error or mean squared error, etc. So we'll talk about only 2-3 things because we have a bunch of other ways of, defining your loss function or cost function, but we'll talk about these predominantly in the interest of time. For the month of Jan, say your model predicted, predicted that the sales will be $100 million, but actually say sales was $90 million. And in the month of Feb, you predicted that sales would be $100 million, but $90 million, but actually say it was $100 million. For the month of March, say your model predicted that your sales will be $110 million, but actually your sales was $100 million. And in the month of April, say you predicted that the sales will be $100 million, but actually say it was $110 million. Now, when you subtract these two predicted values and actual values, you actually get error. $100 minus 90 would give you $10 million. That's the error. 90 minus 100 would give you minus $10 million. 110 minus 100 would give you $10 million. 100 minus 110 would give you minus $10 million. These are all the various errors. If you just take an average of these errors, you get 0. if you just take average or mean of all these errors, you get 0, because plus 10 minus 10 plus 10 minus 10, you get 0. 0 by 4 would be 0. To counter this problem, people came up with mean absolute error. So the expectation here is that you take the absolute values and you get 10, 10, 10, and 10. Right? Then when you take an average of these, you get 10, right? 10 plus 10 plus 10 plus 10 is 40. 40 by 4 is 10. So you got some mean absolute error. And your job is to minimize this. Your algorithm, through your gradient algorithm, right? Gradient descent algorithm wants to minimize this error. And you can also square these errors. When you square, you get 100. When you square minus 10, you again get 100. If you square 10, you get 100. If you square minus 10, you get 100. And when you square the errors and when you take an average of those, you get 100. This is mean squared error. So mean square error also can be used, and your objective is to minimize that. So if you have a neural network like this, you take each and every input, pass it through your network, forward pass, calculate the loss for every neuron, sorry, for every observation. If you have 1,000 observations, pass each and every observation through your network, calculate the loss for each and every observation, then aggregate them to get the cost function. What do you use here? You can simply use as a cost function, mean absolute error or mean squared error, whatever you feel is apt. And then you back propagate and update the weights. You back propagate and update the weights. So back propagation is used to update the weights. However, why are we updating the weights? To minimize this loss, either mean squared error or mean absolute error. Whatever you are using, you want to minimize that. By changing what? By changing your weights. Okay, you keep changing your weights and you keep minimizing your error. And to minimize your the cost function, we use an algorithm called as gradient descent algorithm. Gradient means rate of change. Descent means in the downward directions, because you want to minimize the loss. While this is on one side, loss function and cost function. And this loss or cost function is used for optimization. And what is your objective as part of optimization? Your objective is to minimize the loss or cost. So you want to minimize the loss function or cost function. But to determine how good or how bad your model is, you need to resort to accuracy. And for accuracy also, we can use the same values. And there is also another measure called as mean percentage error. That makes even more sense. Because if you get a percentage error, that the error percentage is say 20%, then the accuracy of the model will be 80%. 100% minus 20%. If you get a mean percentage error of 10%, accuracy would be 90%. This is when your output variable is continuous. So in short, if your output variable is continuous, in your output layer, you would have a single neuron. Point number one. And the activation function would be linear or identity function. Next. You also need to define your loss function or cost function. Usually it is mean absolute error or mean squared error. And also this is for optimization. And your optimization goal is to minimize the loss or cost. And for this, you can use gradient. We use usually gradient descent algorithms. And then to determine whether a model is good or bad, what is the accuracy, etc., we look at model evaluation. And for model evaluation also, you can use mean absolute error or mean squared error. Or you can just say accuracy is what I want to measure. And it will automatically calculate the accuracy values for you. This is when output variable is continuous. There are two more things that we need to talk about. What if the output variable is discrete in two categories? And what if the output variable is discrete in more than two categories? Once that discussion is done, I think our complete picture would be clear. Then we'll proceed further with the discussions. Okay, so time to take a break. It's approximately 3:15. Let us be back by 3:30 and take this discussion forward. Thank you all. Take a break and come back, please. Thank you. Yep. So, hello. Let's move on from where we have left and we will talk further. We already discussed on what will happen if the output variable is continuous and how to deal with it. If your output variable is categorical, and if you have two categories, then people use something called as cross entropy. In that, people use binary cross entropy. They use binary cross entropy when there are two categories. Now, what is this binary cross entropy? What is the formula pertaining to that? How do we get there? Yep, sure. Of course, I can explain in detail because we have time. So for understanding binary cross entropy, one has to first look at entropy. Then they need to understand cross entropy. And then binary cross entropy would be pretty straightforward. So we need to understand now entropy. To help you all understand entropy, I need to resort to a small calculation. Let me pull out the spreadsheet and then I'll talk further. Let me fetch that spreadsheet for you all. And then we can talk further. Just hide a few things. Okay. So let's discuss in further detail. Okay. First of all, we need to understand information theory 101. Hey, what do you mean by information theory 101? If at all you have information like this, come on, it's not picking up. Okay. And on the news channel, sun rose in the east. If at all, some news channel is, putting this in the news and saying that sun rose in the east today. Would you even value it? Absolutely no. You know for a fact that sun will rise in east only. Sun will not rise in west. Okay. Sun rose in the east. And obviously sun will rise in the east. So the probability associated with that is 100% 1 that sun will rise in east. If sun is going to rise in east, and if you really don't value at all that information, then the information contained in that would be 0. But if someone says in a news channel that there was earthquake in Hyderabad, that's a news. What is the probability that there will be earthquake in Hyderabad? Very low. But if it happens, that will become a big news. There'll be a lot of information in it. Okay. So sun rose in the east, probability will be 1, right? And the information content, the amount of information that you're going to have would be inversely proportional to the probability of that event. If the probability is low, information will be high. If the probability is high, information will be low. That's how it works, vice versa. Okay. So if the probability is low, information will be high. If the probability is high, information will be low. This is what we are aware of. All right. Next. For math equation ease, for ease of math calculation, people usually use log. Log of 1 by probability of this. Now, when you want to take this to the numerator, it'll be minus log of probability of event. Okay. This is information content. That means information available in your data, in your content. Then there is something else which is called as expected theory. There is something called as expected value. So let me explain you this as well. So friends, when the underlying values are certain, then to calculate mean, you use your regular mean formula. Average, summation, I equal to 1 until n xi divided by n. However, if the underlying values are uncertain, then you need to bring in the probability aspects into picture. The moment you bring in the probability aspects into picture, the values that you're going to calculate would be called as mean value or expected value. Okay, mean or expected value, which is given as expected value is equal to summation of I equal to 1 until n xi into probability of xi. Why are you bringing probability aspect here? Because it is uncertain. Uncertain means you'll have probabilities involved. For example, if you invest in a government bond, if you invest in government bonds, government might say that on an average, you'll always, on an average, you get 8% return on investment. Now that number is certain. Government would give you because they've promised. On the other side, uncertain means if you invest in TCS stock or Google or Infosys or Facebook, Meta, whatever, then the amount of money that you're going to get back, you're not certain. Since the amount of money that you're going to get back, you're not certain, we use mean or expected value. On similar lines, you have information content, right? So we have, when the values are certain, this is what you get. But then if you want the expected information content, this information, right? When you want expected information content, then the formula would be like this. Here you're multiplying this with probability. Here also you multiply this with probability. Summation of I equal to 1 until n. Since you have a minus sign, I'll put it here. Probability into this value. This happens to be your, this expected information is called as entropy. Expected information content is called as entropy. Okay, now, what do you mean by cross entropy? So I'll erase this part. And let's get into cross entropy discussion. Cross entropy is given as minus summation of I equal to 1 until n pi into log of qi base 2. Okay, pi into log of qi base 2. So, for example, we'll do this calculation. Okay, that would be making our life simpler and easier. Let's say that you have images of cat and dog, and you have a specific image of a cat, which you have given to your machine learning algorithm. You know that this is a cat. So the actual value would say that it's a cat, not a dog. These are your actual values. So when you supply this to your machine learning algorithm, the actual value is 1. Okay, let me call this actual value as P. Then when you supply to your machine learning algorithm might say that there's 80% probability that it's a cat, and there is 20% probability that it is a dog. Now these are your predicted values. So your predicted values, I'm going to name them as Q. Since you have a 2-class problem, you write it as summation of I equal to 1 until 2 pi into log of qi base 2. When you substitute I equal to 1, it becomes P1 into log of q1 base 2 minus, when you substitute I equal to 2, you get P2 into log of q2 base 2. So you just solve it. P1 is 1 into log of q1 is 0.8 minus P2 is 0, Q2 is 0.2. So when you solve it, 0 into this you get some number. That is your cross entropy value. And what is cross entropy? It is a loss function or a cost function. And what do you want to do with loss function or cost function? You want to minimize that. Okay, and that's your optimization. And what algorithm do we use? Gradient descent, because you want to minimize the loss. So if you have a curve, if you have loss function or a cost function, and say here you have weights, what do you want to do? You want to minimize your loss function or cost function value. Okay, that's called as cross entropy. If you have a 2-class problem, this cross entropy is called as binary cross entropy. Determine whether there is cancer or not. Determine whether a credit card transaction is fraudulent or not. For these kind of scenarios, you use binary cross entropy. If you have more than 2 classes, it's called as you call it as basically categorical cross entropy. Categorical cross entropy is used when you have multiple classes or multiple categories. Once again, this is also a loss function or a cost function. All you need to do is minimize these. Okay, this is a high level rational, friends. In a detailed level, we didn't discuss, but then this is a high level rational. Okay, on why we use loss function or cost function. So, Q&A, so that we don't forget what we discussed, right? Suppose your output variable is continuous. Now we'll expand this table, okay, and try to understand further. Or let me put it this way. Suppose your output variable is continuous. Okay. Then in your output layer, number of neurons that you're going to have would be how many, friends? Please, can you resort to the chat window quickly? How many neurons will we have in the output layer? Yep, please, can you answer? Absolutely. You're going to have one neuron. Absolutely. Bang on. You guys are absolutely right. Then, what is the activation function of this output neuron? What will be the activation function, friends? Come on, you should be able to answer this. We have already discussed. Activation function of output neuron. When your output variable is continuous, what do we use? Yes, absolutely. We use linear, which is also called as identity. Wonderful. Thank you so much. I'm really happy that you're able to answer. So that means it got internalized. Okay. Then, what is the loss function or cost function that we use? What is the loss function or cost function we use when output variable is continuous? Wow, good, absolutely. So you are very active. Good. Mean absolute error or mean squared error? Wonderful. What about the evaluation technique, model evaluation? For that, what do we use? It's once again the same, mean absolute error or mean squared error. From this, obviously, you'll get the accuracy as well. Good. This part is clear. The flow is done. Once you understand these, friends, when you get into the programming, it will be just simply give these entries and job done. It'll be that simple. Okay. What if your output variable is categorical? And what if you have two classes? Then what will happen? How many neurons will you have in your output layer? One neuron or two, but usually it is one. So I'll go with one. What about the activation function? Yes, one of our friend has already given that. What is the activation function that we use? Sigmoid, or is it only sigmoid? Or can I use something else? Tanh also, yes. Hyperbolic tangent. What is the loss function or cost function that we use? Just now we discussed, probably 3-4 minutes back. Entropy. What entropy? Because it's not regular entropy. There's a special name given to that. Two categories, two classes only. Cross entropy. Which cross entropy is that? Categorical or binary? Binary, absolutely. So it is binary cross entropy. And for evaluation purpose, you use accuracy. There are multiple ways of measuring accuracy, like confusion matrix, cross table, and all that. We will get into that when we actually solve that specific business problem. Then, when you have your output variable, which is categorical, and if it has more than two classes, then suppose you have 10 class problem. Then how many neurons will you have in the output layer? In the output layer, how many neurons do we have? 10 neurons. Because 10 classes. What about the activation function? Softmax, absolutely. We use softmax activation function. And when it comes to loss function or cost function, what do we use? What do we use as part of loss function or cost function? Categorical cross entropy. Wonderful. Yes. It is categorical cross entropy. And then obviously you use confusion matrix or cross table, etc., to get the accuracy. Wonderful. So this is how you calculate it. Okay. Next. Now, when I say cost function or error function, you'll be easily able to understand. Okay. For output variable, what is the loss or cost function? Output variable categorical, two categories, multi-categories. How do you actually proceed further? And if you have a single input or a single weight, then if I were to draw something like this, probably you'll understand. But if you have two inputs, two weights, these are like W1, W2 in that way. Then the error surface will look like this in two-dimensional space. And cost is given using J, cost or loss. That's how it is represented. Okay. How are the weights initialized? You have your input layer, say you have your hidden layer and an output layer. When the algorithm gets started, how are the weights initialized? Randomly. Randomly, the weights are initialized. When the weights are randomly initialized, you might get a loss like this. Randomly somewhere, the loss is plotted for the weights. So if you go like this, probably this is a weight here, and this is the weight here. Okay, imagine I'm going right to the bottom, in a vertical direction. So if you have 2, this is how it would work. But in real world, you'll have multiple inputs, not 1, not 2. You might have 5, 6, 10 in that way, right? So visualizing itself is not possible. So rather than take 2 inputs and show you, I'll take one weight, one input. Then the curve would be easier, right? If your weights are randomly initialized and say this is your loss function or cost function, then what do? You update the weights and you reduce your loss or cost. Then again, you update the weights, again you minimize, again you update the weights, again you minimize, again you update, again you minimize, again you update, and again you minimize until you get to the bottom. If you have only a single curve like that, quadratic curve, you know that you have only one minima, and that would be called as a global minima. However, in practical world, it won't be like that. It won't be a simple quadratic thing. It'll be like this. When it is like that, you'll have multiple minima. And out of all these minima, you want to get to the least of all these minimas. Right? When you have multiple minimas like that, all these would be called as local minima. The one which is the minimum out of all these minima is called as a global minimum. Okay. Okay. If the weights are randomly initialized here, then slowly it will move down and come down the surface. So, at time period 1, say this is your weight and this is your loss. Then next iteration, your weights get updated and your loss gets reduced. In the next iteration, again your weights get updated, your loss gets reduced. In the next iteration, again your weights get reduced and your weights get updated and the loss will be reduced. So in 1, 2, 3 iterations, you're reaching the minima in this case. Okay. But there is issue with the local minima. What is that issue? It really depends on how the weights are initialized. If the weights are randomly initialized at a different location, say instead of initializing here, your weights get initialized here, then what would happen? You might get into a different minima. Here, if the weights are initialized here, you're getting to this minima. If the weights are initialized here, you're getting to this minima. Okay, so now that we understand this also, let's get into some visualization to understand this in an even better manner. So we have a backpropagation algorithm. Okay, for now, for our ease of understanding, what I'm doing is I'm merging the integration and activation function into one, just for our understanding. Okay. We will take this as an example where we have two inputs. For now, I'm ignoring bias, but do you know what? You'll have one bias throughout. You'll have a bias throughout. You'll have a bias throughout. Okay. You'll have bias throughout. Ideally. For now, let's ignore that. Assume that we started our algorithm wherein you have two inputs and one output. How are weights initialized? First, randomly the weights are initialized. So we have x1 and we have x2. And you have weights which are randomly initialized. And here you will have integration component and activation component. Integration and activation. So W1 x1 plus W2 x2. This would give you your summation integration. Then when you pass it through your activation, you get an output y1. Okay. So you got y1. Next. When your inputs go into this neuron, again here, you will have the integration and activation. So W1, this weight into this input, plus this weight into this input, would give you the integration part. Then when you pass it to your activation, some ReLU activation function, assume, some activation function, then you get an output. Say that output is y2. Then from this input, you have a weight. From this input, you have a weight. So this weight into this, plus this weight into this weight into this, plus this weight into this, would give you the integration component. Once you get that integration component, you move on to the activation. Then you get an output which is y3. Then these weights are also randomly initialized. So you have the integration. W1 into y1, this weight into y1, this plus this weight into this, plus this weight into this, would give you the integration component. And then you pass it to your activation, then you get y4. Then this weight into this, plus this weight into this, plus this weight into this, would give you the integration. You pass it to your activation, and then you get y5. Again, move forward. Because what are we doing now? Forward pass. Forward passes going on. Then here, these two weights are also randomly initialized. All the weights are randomly initialized in the forward pass first time. So this weight into this, plus this weight into this, would give you the integration component. And then when you pass that to the activation, you get the final output. So this is your predicted value. Now, when you subtract this predicted value from the actual value, so say you have the actual value and you have the predicted value, when you subtract those two, assume that output is continuous, okay? So if you subtract those two, you get loss. Say you're just using a loss or a cost. For all the observations, say you got the loss and then you aggregated to get the cost function. And say we are using the cost function, which is mean squared error. Assume for now. Okay. Then what do we do? Once we have a loss of so much, what should you do? You have to go back, which is called as now backward pass. And you'll have to update the weights. This process is called as back propagation. Okay, using back propagation, what do? You update the weights. We update the weights using back propagation. All right, then you come back, update all these weights. All right, but to update the weights, you have some loss or cost, and you know that this loss was contributed by all of these neurons. So you need to give them a penalty. This is like, say, your manager, because of the error in the output of your model, project management model, has, he has received a cut in the salary or in the bonus. So this manager will be very annoyed, right? He'll come back rushing and he would say, probably team leads, because of both of you, there was an error. Since because of both of you, there was an error, I want to penalize you. I want to put a penalty on you. My bonus got deducted. I will also penalize you for this. Then this team lead might say, F4, that, hey, do you know what? My contribution was only Y4. Only Y4 I've given you as an input. Then team lead might say, okay, take back this much weight, Y4 into this weight, right? So this much weight of the error, I'm going to give you as a penalty. So that much amount of bonus I'm going to deduct from you. Okay. Then this team lead also might say that same is with me. Don't penalize me completely because I contributed you a weight of W56. Okay, don't worry. This manager would say, for you, penalty will be W56 into this. So delta 5 take as penalty. Now the team leads are very unhappy. These two, they are like, who are those team members who have done mistake? Let us go and put a penalty on them also. Okay. And they'll put a penalty now. This team lead will go back to this guy and say, hey, how much input did you give me? Some weight here. And you know what? This guy has also given an input to this team lead. So then what you do is, let's take the example of this team lead, this team member. Both the team leads, this guy has given input to W24 and W25. So W24 into this plus W25 into this delta 5 would give you the overall weightage of error that this guy has to take, or penalty, rather, not weight, penalty. This was my one. Okay, next. For this guy also, W34 into this and W35 into this. That's so much of penalty would be given. Okay. And so on and so forth. For this guy also, same penalties would be given. Then finally, you start updating the weights. To update the weights, the same formula is applied. New weight is equal to old weight plus eta value, which is also called as learning rate. Eta value is also called as learning rate. And this value ranges from 0 to 1. Into the error, into input. You apply that to each and every weight, and your weights will be updated in this way. All the weights will be updated. Now with these new weights, once again forward pass, calculate the loss, again back propagate, update the weights, keep doing it. Rinse and repeat, continuously keep doing that. Okay, and ultimately, once the back propagation is complete, your algorithm will stop. You might say that stop the algorithm after 10 iterations, or stop the algorithm after 20 iterations. You give some number. Or you might say that if the error reaches 1%, stop. Okay. So a few things that we need to understand now. What did we understand? That we will have input layers, input layer rather, in which you'll have a number of neurons. You'll have a hidden layer, and you'll have output layer. Okay. Is my voice clear? Please, can you confirm? I don't see any disturbance. Is there any disturbance? Let me mute everyone. Clear? Okay, fine. Let me proceed further. Maybe internet issue at your end, friend. You need to check that because everyone else is saying that voice is clear. Okay. So in the output layer, you can have multiple neurons. You need not always have a single neuron. You can have multiple neurons as well. Okay. And you need not have a single hidden layer. You can have multiple hidden layers also. The number of neurons in each hidden layer need not be same. There can be different also. Okay. Next. I think there will be a question for you all now. Okay. There are two architectures that you see. Once you take the data, you supply the data to your inputs, and then you get the output. Here also it's the same, but the only addition is that you have hidden layer with two neurons. This is fine, but now can you tell me if I say this is architecture A and if this is architecture B, which of these two architectures, okay, which of these two architectures is called as perceptron algorithm? A, absolutely, right? A is perceptron algorithm. Why is it called as perceptron? Because there are no hidden layers. Perceptron algorithm has no hidden layers, and it will have a single neuron in output. In output. Then B obviously is multi-layered perceptron. In a multi-layered perceptron, you will have hidden layers. You can have 1, 2, 3, 4,000, how many ever hidden layers of your choice. You can have a lot of neurons in your hidden layers. And in the output also, you might have a single node, or you can have 2 nodes, or you can have multiple nodes. Great. Next. This is how the calculation happened, just to tell you that we have taken the inputs, we have passed it through the hidden layers, you get the predictions, compare it with the actual values, you get the loss. With that loss score, go back and update the weights. And the goal is to minimize the loss or a cost function. There's one amazing way of manually calculating. I'll refrain because we need to, talk about the practicals also. So when it comes to deep learning libraries, the world started off with Torch in 2002 itself. Then came Theano, then Caffe, etc. But TensorFlow was a revolution from Google. Then in the same year, Francois Chollet has come up with Keras, and now we have PyTorch. So from a practical standpoint, we would first use TensorFlow Keras, because now Keras is an integral part of TensorFlow. And then we'll also look at PyTorch. Okay, so we have NVIDIA, because when you run your deep learning algorithms, you need GPUs, graphical processing units. However, if you do not have a GPU, don't worry, friends. You need not worry absolutely. Why? Because we will make use of Google Colab. And within Google Colab, even in the free version, you have GPUs. Even in the free version, you have. Okay. So you have TensorFlow, Theano, PyTorch, Caffe, etc. Okay. So when you look at deep learning libraries, scikit-learn is used by majority of them, because a lot of the people are still using traditional machine learning algorithms. Then you have TensorFlow, Keras as well. Okay. And of course, we have XGBoost, PyTorch. PyTorch is picking up, so we need not worry too much. It would pick up very fast. Okay. And if you have Keras and TensorFlow, as I've told you, TensorFlow is a low-level programming language. So you need detail-level programming in order to handle that. And Keras is high-level. So even if you're a new person to deep learning, you can still do that. And these libraries can run on CPUs. These libraries can run on GPUs. And also the libraries can run on TPUs. Tensor processing units. Tensors are special units which Google has come up with. And this is from TensorFlow standpoint. Now, is deep learning a holy grail? Will it solve all the problems on the planet? No. Okay, you need to decide which loss function you want to use. Different times when you run the algorithm, you might get different results because the weights are initialized in that way. It is black box, so you don't have any explainability in that. Since each time you run, weights are randomly initialized, it's not easy to reproduce. You cannot interpret the results. all these, there are a lot of ablation techniques. Ablation techniques means how many hidden layers do I need to choose? How many neurons do I need to use in each and every hidden layer? What activation functions do I need to use in hidden layers? All these are at a very high level, right? I mean, they're not concrete. You need to experiment. There are no concrete ways. So with this, I mark the end of at least the initial part of theory. And there's one small theory left. We will look into that also and we'll proceed further. Here we go. This is what Rabindranath Tagore says. The butterfly counts not months, but moments and has time enough, right? So make every moment of yours count, friends. And thank you all so much. I would stop here. I would highly recommend you all to go to this mind map and have an eye on the mind map, because we'll be adding newer things always. So let me take your attention here. So when you go to our website, you would have an option called mind map. When you click on the mind map, do a drop down, go to either certificate program in data science or practical data science, whichever works. And you just need to double click to expand, double click to collapse. And we are adding more and more information on a daily basis. So you can be rest assured that you'd get the most updated stuff always. Okay. And of course, our YouTube channel has a lot of stuff available. Please subscribe. All the deployment models and a lot of interesting things are anyways there. Yeah. Thank you. You have the attendance sheet. You might want to